All right. Good morning to you fantastic AP students that are sticking it out. I'm entering the fifth review session, sticking it out for sure. But I'm proud of your efforts, and they'll surely pay off. Quick recap: ending the fourth review, we were in circular motion, horizontal circular motion. Two most common problems. The car going around the rotary, thinking of static friction as a centripetal force, or a ball tied to a rope swinging around a circle where the tension is the centripetal force. Now we're turning our attention to vertical circular motion, or what's sometimes referred to as motion along a vertical plane. The other would have been referred to as motion along a horizontal plane. Okay, we're going to look at the spinning bucket of water. You probably recall. I'm not really drawing that right. Right down here like this. A spinning bucket. It's got water in it. It's got a rope tied to it. This is a rope again. And then somebody stands, like I've done this before in class, and then you just zip it around in circles. Boom, boom, boom. At the top, if it's going at a minimum speed or higher, water won't fall out. And we certainly will tackle that. And majority of their questions, when this turns up, is referencing the bottom and the top. Very rarely do they reference the sides. Okay, inward forces plus, outward forces minus. There's two. There's a tension force up, and you might be inclined to draw the gravity force down like this, but that would be an equilibrium, right? That would be a balance. That what my free body diagram is showing would be balanced forces, and that cannot be true, right? The forces can't be balanced. When you're in circular motion, the forces need to be unbalanced. There needs to be an extra amount of force in the direction of towards the center of the circle in an amount of mv squared over r. The net force, the unbalanced amount of force, has to be equal to mv squared over r. That's of the centripetal force. It's an extra unbalanced amount of force. It has to point towards the center, and as long as that occurs, you will maintain your circular path at a constant speed as you continue around the path at a constant uniform radius. So in this type of problem, you simply put in tension, which is up, minus mg, which is down, because of these. This is down, since it's away. This is plus, since it's towards, equals mv squared over r. That's it. You solve for ft. Usually their question is about ft. The question is about the tension in the rope at the bottom, most of the time. mv squared over r plus mg. Or you can write it the other way, which I usually like to write it the other way, which is mg first. Just remembering, that if this bucket is not swinging, you stop swinging it, and now the person just lets it dangle straight down, what should the tension of the rope be? Mg, right? Because it's just now dangling, sitting there, hanging from a rope. In that case, V would be 0. And when you put in 0, that term goes away and it reduces down to something that you already know, which it has to do. That's all more comprehensive formulas must be reducible to simplest cases as well, and inclusive of things that are more complicated. So that's the way I like to write it. Could you technically factor out your V? I didn't mean to say that. Could you technically factor out your M that's in both of those? Yes, you could. Notice that now what you're summing up are the acceleration due to gravity, g, and the centripetal acceleration, right? B squared over r is the centripetal acceleration. Those are being added together because two separate types of accelerations that are occurring, and the tension created in the rope involves both. So if they were to let me also point, well, I'll come back to that formula. So you could certainly note that down. It's one of the important ones. This is at the bottom. It's only at the bottom. And we have to talk about at the top. And when we talk about the top, we end up determining what the minimum speed at the top is. And then we have to come back to this formula because sometimes they say when the thing is being whipped around at a minimum speed, what will the tension at the bottom be? I don't know why I just lost my. Sorry, just trying to get my whiteboard back up. Just Seem to lose it. Okie dokie. Wish I could just pause this and then, but there's no pause button on these recordings, unfortunately. Try one more time. There we go. Back. Okay, so I was about to erase this. And I'm just saying that we're now going to turn our attention to the top. And there we have to derive a formula for the minimum speed so that water doesn't fall out of the bucket. It's the most common thing to teach. And then come back to the bottom and or the top once we have the minimum speed equation for how minimum speed it has to be moving so water does not spill out. Then we're use that formula in the either the bottom or the top to derive formulas for the tension. Top of when you're moving at that minimum speed, or twice the minimum speed, or 3 times the minimum speed. So I will try to do that as best I can, as quickly as I can. At the top, both forces are down. Fg is down, Ft is down. Those are both positive, plus, plus. The net force is mv squared over r. So we end up with Ft plus mfg equals mv squared over r. The one that's re-expressible is Fg as mg, of course. And then if we're solving for Ft, we would just move our mg over to the right side, and we end up with mv squared over r minus mg. This is at the top. This is the magnitude, of course, of the tension at the top. Notice as we compare it to the other one, the magnitude of the tension at the bottom was mg plus mv squared over r. Notice this. Notice that they switch roles. One's in the top, you have a minus mg. Notice, and then in the bottom, you have a plus mg. But they both start with. I mean, if you wanted to write them the same way, if it's easier to remember it that way, don't have to cross them like that. You could write it as mv squared over r plus mg. Then maybe that's easier to remember. The same format, mv squared over r plus mg or minus mg. Just know at the bottom is the most tension, right? And that's how you can think through. Should it be for the bottom a plus or the minus? There's always the greatest tension at the bottom. You're just being zipped around. Your weight is essentially pulling you down, and you got the rope pulling you up, and you got the greatest contrast in forces, and that stretches the rope the most. Right? At the top, it's not the case. At the top, the tension in the rope down, the gravity force is down. The fact that gravity is pulling down when it's at the top essentially loosens the rope. Right? When something's zipping around upside down like this. If this was in outer space, let's say no gravity, then you're zipping around just like this, then there'd be some amount of tension in this rope. But then you say, but in a gravity field, gravity's pulling down on this. That should cause our rope to kind of loosen a little bit, right? Pulling it away, of course, we know would tighten it, more tension, but a downward pull should loosen it, right? And then the opposite can be said when it was down at the bottom. You know, in a zero gravity field, you'd be zipping it around, and at the bottom, there'd be some tension. Somebody comes over at that moment and pulls down a little harder there. What should that do to your rope? Rope should get tighter, right? There should be already have been some tension just because you're going in circular motion in a no gravity field. As soon as you introduce gravity to it, gravity is that extra downward pull. What's that going to do to a rope that's tied over here in the center? You're pulling away from it, it's going to increase the tension, right? So that's the way you can remember that. Tension is always greatest at the bottom. Surely they do usually assess that somewhere. Exam. Then what we do is we reference the top to decide what is the minimum speed so that water does not spill out of the bucket. At the top, if you are actually going at remember this, tangential speed is to the side. But if you're going at just the minimum speed, the water does not come out of the bucket. If you're going faster than that minimum speed, the water still doesn't come out of the bucket. If you're going anything less than that minimum speed at the top, water comes out of the bucket, lands on your head when you're doing this trick. So their question is usually, derive a formula for the minimum speed so that water does not come out of the bucket. Remember, if you're actually going at the minimum speed, exactly at the minimum speed. Though the rope is not tight at all. At the exact minimum speed, this rope goes slack. Just it reduces to a tension of 0 for a fraction of a second. And the moment it passes that midpoint, the tension returns. And then the tension increases as it goes down towards the bottom with a maximum tension at the bottom. And then the tension decreases as it comes up, and then it would be 0 tension at the top. And then more tension, more, all the way down to the bottom, the most at the bottom. Which, if we graphed it out, which we did in class one day, a tension versus time graph, what did we see? We saw that. Interesting. That could be modeled with, cosine or sine function, just like for periodic motion, with the amplitude being the max tension. Because of what I just said, a 0 at the top, and technically, if it was 0 at the top, technically you'd have to have you'd have to have this touch to 0, right? If this was the starting moment was actually at the top, then it would actually go like this, right? The first moment at the top would be 0 tension, and then as you go down, this force would be increasing a lot up, and then right round and round it repeats. So know that at minimum speed, the rope goes fully slack and there's no tension. And that means we can use our top formula and just stick in 0 for the tension. And now as soon as we put in 0 at the top for Ft, then we're immediately referencing the minimum at Vmin. That's the minimum speed, because it only goes to 0. The tension only goes to 0 when you're going at that minimum speed. So now we just solve for that. So we'd end up with m Vmin for r squared equals mg by just moving mg over to the other side. M and m go away. It doesn't matter what the mass in the bucket is. Rarely mass matters. Sometimes it does, of course, but a lot of questions it doesn't. Doesn't matter if you have 2 cups of water in there or 2 gallons of water in there. As long as you're going at that minimum speed, in both cases, the water won't fall out. You don't have to make adjustments to your speed based on how much water or weight or mass is in your bucket. And what do we get? For the Vmin, we get Vmin equals the square root of Rg. Super useful, easy to remember in my opinion, because it's pretty short. Minimum speed is the square root of r times g. R is that, again, remember the distance, length of the rope. It's the distance from the center up to wherever the edge of the circle is. So if we wanted to know what is the tension in the bottom when this thing is moving at a minimum speed, and they're going to say it moves at a constant speed, round and round it goes at a constant speed, but the constant speed it's moving at is square root of Rg. It's moving at the minimum speed. If that's the case, what is the in the rope at the bottom? We would then have to sub this in, this expression for the minimum speed, straight in for V, right? What would we get? Ft at the bottom at Vmin, assuming that we're moving at the minimum. The Vmin is, again, referencing the top. It's referencing the minimum speed so that water doesn't fall out of the top. And now we're going to assume it just maintains that minimum speed around the whole circle. And once we understand that, we then are asked the question, if that's the case, what will the tension at the bottom be? It passes through the bottom, moving still at the minimum speed needed for water not to fall out at the top. We get m, and now we're just subbing in root Rg squared over r plus mg. What do we get? M, because again, this is our expression for Vmin. So when you square root Rg, you end up with just undoing that, square root over r. And we get the r is here to cancel. And we're left with mg plus mg, recognizing mg, I hope, as weight. So that means 2 times the weight of the bucket, right? So that result is at bottom, tension at bottom, mg plus mg is 2 mg, or 2 times the weight. If moving at Vmin, remember these are all referencing Vmin, assuming you're moving at Vmin. And that would be it, 2 mg. Could you technically apply that same idea to the top? Could they have asked, well, we know it's actually, take that back, it's 0 tension if you're moving at Vmin at the top. However, they could also ask, and sometimes they do, what if we're moving what if we're moving 2 times the minimum speed? If the minimum speed to not fall out at the top is 20 miles per hour, let's assume you're moving 40 miles per hour. You're moving twice the minimum speed, twice the speed necessary to prevent water from falling out. How would we do that? Then we would just say V is equal to 2 V min, 2 root RG, because our root RG is representative of that minimum speed, right? And we could repeat that problem, and they could say, what's the tension at the bottom now? And just plug it in for V again. M, you just have to put 2 RG in for V min over R plus mg. And notice that I'm forgetting that I have to square it. When I square it, you have to square everything that's inside there, the 2 and the root RG. So you'd end up with M times 4 RG over R plus mg. And your R's cancel. And now what are you left with? First term is 4 mg plus mg. That's a total of 5 mg, 5 times your weight, right? So that means at V equals 2 V min, at the bottom, FT would equal 5 times your weight, 5 mg. So for me, if it was I was being swung around 200 pounds, then it would be 1,000 pounds of tension in the rope at the bottom if I was going twice the minimum speed necessary for me not to fall out of myself. I don't know if that doesn't make sense. At the top. So that's kind of how we do that. We use the square root of RG, and I don't recommend trying to memorize all of. I mean, you could if you wanted. I guess just remember that so in case you don't want to derive it, at V min, FT is 0 top, FT is 2 mg at bottom. And then they might reference, at 2 times V min, FT equals 5 mg at the bottom. And I will tell you the result is 3 mg at the top. Because if we did it for the top, it just ends up, this is all the same, just that it becomes a minus, right? So we'd end up with 4 mg minus mg, which would be 3 mg, right? So you could think of it as just doing 2. You could think of it as doing n. Trying to think of an easier way to write this. Square root of RG squared. N could just be how many times faster you're moving. Am I writing that right? NRG over R, I guess. And that's a plus or minus mg, depending on if you're at the top or the bottom. So you'd end up with just n squared, right? Rg over R plus or minus mg. So if you wanted to just kind of write it as an algorithm, where n is either 1 times the minimum speed, 2 times the minimum speed, or 3 times the minimum speed, then the ft would, the r's went away, would be n squared g plus mg. Now, the plus or minus, just remember that plus is the at the bottom and minus is at the top. So in an example, if you were going 3 times the minimum speed, what would the tension be at the bottom? 3 squared g, and we know at bottom it's a plus mg. That's 9. I'm missing my m there. Yeah, 9 mg. What am I missing? Yeah, sorry. There's an m. I would need an m in this algorithm. N squared times mg. Sorry. N squared times mg. So that would have come out as at 3 times the minimum speed. We're just putting in 3 for n. So 9 mg plus mg, wow, 10 times. It would be 10 times my weight. If I was going 3 times the minimum speed, and this, since I have a plus in it, it's the bottom. If it was at the top, all I do is 3 times the minimum speed, I would take away my plus and put a minus. 3 times my minimum speed is now 9 mg minus mg is 8. The difference is between them is always 2 for any particular speed. The difference between the top and the bottom will be 2 factors of your weight. All right, moving on. So now we're going to quickly talk about some similar ones that relate to this. You have your Ferris wheel problem where this thing, goes round and round. You've seen this before as an open response question because I know I gave it to you at some point. In this case, remember the gravity force is always down. These are all FG vectors. And usually this there must be some inward force. There must be some centripetal force. I'd have to really think about what it is. I guess it would be friction from the seat probably, or if it's created so that the back of the seat is pushing you in that direction. Well, I know I have to think about how the person is situated in that there's something that the person's body's touching would have to be pushing them or her always in this direction. But I will point out, usually this is not in relation to centripetal forces, surprisingly. Usually it's in relation to the normal force versus the gravitational force. So know that at the bottom, again, there would have to be more normal force than weight because there has to still be a centripetal force, an extra amount of force towards the center. Right? The unbalanced amount of force, an extra amount has to be towards the center. Again, usually their questions are about the top and the bottom. Don't really need to draw all these. And then at the top, the same idea. At the top, you end up with, but you'd have to have more weight down and less normal force up because the extra amount of force has to be down. The centripetal extra amount of the unbalanced of those two has to be in the downward direction, right? Because your acceleration vector would be down towards the center. Acceleration vectors, remember, are always pointing towards the center, and the centripetal force vectors are always pointing towards the center. And that centripetal just references the unbalanced amount of force from the normal forces that you're used to, like this, Fn and mg. So usually they would ask, what is the normal force at the bottom? It's no different. It's just the same thing that we were just doing. We just say that the net force equals mv squared over r. Let's look at the force at the bottom. Fn would be plus, mg would be minus because it's down. I'd write Fn minus mg equals mv squared over r. Oh, wait a minute. Isn't that the same exact answer we got from before? Yes, it is. V squared over r plus mg. What was it before? Well, the normal force was the tension in the rope, right? The thing that was at the bottom, at least, the upward force for the spinning bucket was an upward force was tension. Here, the upward force is the normal force. So all we're doing is taking the same exact formula, removing Ft from this and plugging Fn. Will it be the same for the top? Yes, it will. And I'm not going to bother taking the time to derive it. It'll be exactly the same, right? So this is at bottom. Fn at the top would be mv squared over r minus mg. Are they going to reference going like twice some speed or 3 times? No, that's usually just a reference to the spinning bucket. But they would ask you how to model this for sure. Free body diagram it for sure. Remembering going around the rotary, going around the Ferris wheel, they'll probably give you something about period. And to get this V, sometimes you have to work for it. Making you do a calculation. R is the radius of the Ferris wheel. Or I think in the open response question you guys saw way back when, it actually started with just showing you a graph of this person's horizontal position versus time, since as you go around a Ferris wheel, round and round, technically your horizontal position goes to the right and then back to the left, and then to the right and then back to the left, depending on where you are as you go around that circle, right? And they said, see, here's the horizontal position of the person as a function of time. And in this case, you would have had to go like this. If this was the 2-second mark and this was the 3-second mark in the simplest case, you would say, okay, crest, this is a period of 1 second, and that's what they expected you to do, because they gave you the radius, and then you plugged in the period. I'm sure it wasn't exactly 1 second, but you were able to figure out the velocity by doing 2 pi over t, but they didn't give you t other than, hey, look at the graph and figure out t on your own first, right? And then that gets folded in here if they're asking a question about the normal force. All right, done with that. Now we're moving on to the loop-de-loop. It's all very similar, which is why these are going to go faster, at least these last couple. Something comes down a track and then arrives up at the top, heading in which direction? In this direction. Tangential velocity vectors that way. Free body diagram it. The normal force would be down. The gravity force would be down. I'm not writing one of them longer than the other. I'm just indicating there's 2 forces that are down. At the minimum speed, which not surprisingly they ask about, what's the minimum speed for this thing at this top point, point P on the diagram, so that, if you want to think of it as water, it's a container that's sliding down, got water in it. What's the minimum speed so the water doesn't fall out? Or it's a person in a car, amusement park ride. What's the minimum speed that the person has to have in this little cart so that the person doesn't fall out of this amusement park ride? Doesn't matter what the object is, of course. Same question. We already know it. Right? V min equals square root of RG. It's the same thing as the bucket. Doesn't matter whether there's a bucket here and a rope, or whether the downward force that we're talking is the tension in the rope, or if the downward tension is just the normal force. They're both downward. They're both playing the role of centripetal force. In this case, at the top, the normal force and the tension in the rope for the spinning bucket is the same thing, right? So this is the same exact, I'm not going to derive it again. It's exact, you just need to know this is the formula. V min equals square root of RG. If you're going at that minimum speed, what will the normal force be? Well, if you're going at the minimum speed for the spinning bucket, what is the tension in the rope at the top if you're going at that minimum speed? At the minimum speed, what happens to the rope? It goes slack just for a fraction of a second, and then tension builds the moment after you pass through the middle. Well, that means at the top, again, there was no downward centripetal force. The only centripetal force was gravity. That's the idea. When you're moving at the minimum speed, like we were talking about before, for the bucket, it's upside down. If there were 2 forces that we were thinking about for the bucket, which was both the tension force and the gravity force, and we say at the minimum speed, there's no tension in the rope, that means this force is gone. That means the only centripetal force, because prior to that, you'd be thinking, hey, I guess I have 2 centripetal forces here, right? And the sum, the net of those is equal to mv squared over r. But in those V min scenarios where it's moving at a minimum speed, the rope goes slack, which means the only centripetal force is gravity, right? And then you're just essentially setting mg equal to mv squared over r. And you'd realize that g is v squared over r, right? G is v squared over r, and that's why we get, when we do this, v min equals the square root of rg. That's what you get algebraically from what was g equals v squared over r. Just move your r over to the other side, you get rg, then undo it by square root. But numerically, like 10, like just pointing that out, like whatever v min is squared over r is 10 or 9.8. It's or I could just point out g is the centripetal acceleration, because v squared over r is the centripetal acceleration, right? So at the minimum speed, the only centripetal force is your weight, and the only centripetal acceleration is g, just the Earth's gravitational field. Be aware of that. So at this particular case, again, if you're going at a minimum speed around the loop-to-loop, if we know that the rope in the other problem goes slack, that means that the person, again, would separate. You might remember I showed you the video, a slow motion video I posted on Google Classroom of my ball. I captured it with my phone, and you could see it clearly separated. We could hear shh. You could hear it sliding along the track, and then right at the top, the sound went silent for a brief second. You could see it just barely comes off, and then catches again here. You hear it again coming. It was evidence that what I was saying was true. Right at that minimum speed, it loses contact. Well, if this is contact, what is the normal force if you're not touching? Normal force is the force between the object and the track. And if you're not touching the track, then the normal force is 0. Right? So if we were doing this whole, Fn is down, Fg is down, then, get the same, you get the same result. Fn, if they said, model it, Fn plus mg equals mv squared over r. They're both towards the center. That's why they're both plus. And then if you just solve for Fn again, you get mv squared over r minus mg. Just plugging in mg for Fg and then moving to the right as minus. It's the same thing, right? It's the mv squared over r plus or minus mg, but at the top, right? And again, if you're going at the minimum speed, then, well, the normal force is 0, and we continue forward and go like this, and then we see that the masses don't matter, and then if we, I don't know, move the g over, we end up with what we had before, v squared over r. This is now the minimum speed. That's it, right? One thing you need to know is this. They're not going to say if it's going twice the minimum speed or 3 times the minimum speed. And just know that that still applies and know how the free body diagrams work. Also know that at the bottom of the loop-de-loop, it's all kinetic energy, right? Or in the real problems, usually they start them up at a track, and you would need to know, okay, starting up at some height, so the initial potential energy is mgh, and you'd say that the initial mechanical energy of the block Earth system, don't forget about the block Earth system, right? Potential energy has to involve the Earth because it's the potential to fall towards the Earth. You can't say it's just the potential energy of the block. Potential energy is the potential to fall towards something, so you have to mention the thing that they're falling towards. It's falling towards. That's why I would say the block Earth system. If they said, what is the mechanical energy of just a block? You're supposed to say 0 at this point. You know how I feel about that. If they say the mechanical energy of the Earth, of the block Earth system, at the top, of course, it's just potential energy. And then we're going to release it, and it's going to go around this loop, right? So how much kinetic energy would be at this point? All of it, mgh. Whatever the initial potential energy was, it would be all kinetic. Bottom, right? At the top, it's moving to the side. So like projectile motion in 2D, at the top here, is it just potential energy? Like, no, it's cruising along. It's got some sideways Vx, and therefore it has some kinetic energy. It's up in the air. It has some potential energy. Total mechanical energy is the sum of both. Is that different than now? When you're going around this loop and now you're heading to the left, you'd say, no, it's the same idea. How would we express the total mechanical energy E? You would say it's kinetic energy at the top plus the potential energy at the top. And you would have to think, again, be aware of this little trick. If this is R, and then that means this is R, then what is technically the height at the top? 2R. Oh, that's a little trick. That's a little trick that you can do, right? It makes sense. You're at the top of the loop. You're at a height of 2R above the ground. This could be 1/2 mv squared. This can be mg, technically 2R, mgh, but sometimes you end up having to write it in as 2R. And technically, if you're moving at the minimum speed, if they give you a problem where this thing is moving at the minimum speed, then you could put in root RG, square root of RG, because root RG is, again, the minimum speed. You could plug that in there, and that would be, again, an expression for the total mechanical energy, at least at the top, right? And then as it comes down the side, that potential energy starts turning back into kinetic energy. And then when you're at the bottom here again, then you return to that point with the same speed that you had when you first arrived. The first time you arrive at the bottom is when you just came down the hill, right? When all the mechanical energy was in the amount of mgh. Then you going around the loop just takes that amount of energy, mgh, and now splits it into these, right? And then as you come back down the loop, all of this energy, all of the mechanical energy, which again is this, just turns back into kinetic energy. And you're at the bottom with the same speed. So originally, if you came down this hill and you had a speed of 20 meters per second at the bottom, you go up, 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 you slow, 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 slow. Then you go around, speed up, back. And then when you hit the bottom, you'd be 20 meters per second again, right? Because the total mechanical energy is constant, right? Assuming there's no loss of friction, there usually isn't. that means there's the total mechanical energy is not changing, right? For sure, the potential and kinetic energy is changing as this thing goes from the top around. That's pretty clear. But the potential, remember, I mean the total is not changing. Let me lastly make one little quick comment about this. That technically in this problem they could fold in two. They could say it starts up here, and now we're talking potential energy mgh. Just pointing this out, and then they can fold in energy and circular motion all into the same problem. So I want to point that out, that technically at this particular point here, you again would have some mg2r, and that's not good. This would have had to been shown up starting up higher than or higher than the top of the loop. So it's starting up here, let's say, and mgh goes, h goes all the way up to where it's starting, all the way at the top, all the way up here. And so the potential energy would again be mgh initially, and there's some loss of potential energy, delta H, between those 2 points is there. My point is that if they were, if you were modeling this with, if you recognize the normal force again is down here, the gravity force is down here, then technically modeling the forces there, you would still say Fn, they're both towards the center, so they're both plus. Fn plus Fg equals mv squared over r. And you'd have Fn equals mv squared over r minus mg, as we had before. My point is that this v right here, sometimes you end up doing kinetic energy and potential energy stuff from modeling the conservation of energy, that the total energy at the top and the mgh initial would have to be equal to the, if we're referring to when we're passing through the top of the loop, knowing that we started at the top of the hill and now the second point is at the top of the loop. The total mechanical energy was all potential, and then we'd have 1/2 mv at the top of the loop squared plus mg, and in for h we're putting 2r, right? So all I'm trying to point out is that there is a connection sometimes between the energy modeling and the forces modeling. And they might ask you about that. And so sometimes you end up taking this v from the forces modeling here and sticking it into the energy model. So just be aware that that sometimes happens. All right, I don't think I have anything else to say about that. I am now going to continue. We're going to talk about space stuff. All right, let's go. Let's do this and do as much as I can. So now we're going to talk about planets, two planets that are some distance apart. Usually we call that R, planet 1 and planet 2. The gravity force between them is mass of planet 1 times the mass of planet 2 divided by the distance between them squared. That's considered Newton's universal law of gravity. Universal because it actually works for everything. I could use the same formula to compute my weight, where m1 would be the mass of the Earth, m2 would be my mass, r is my distance from the center of the Earth, which, well, is just the radius of the Earth. G, it's very rare that you would need to use that. Certainly don't bother memorizing it. I think it's on your equation sheet. But I could plug all that stuff in. And, I get 800 newtons. Like, cool. Like, when I just do my mg, just my mass of about, 80 kilograms times g, I know that I'm about 800 newtons. And when I do all the information in here where the two objects are me and the Earth, and I put the distance between the center of the Earth and me, surprisingly coming out of that formula is 800 newtons, right? It's proof that this is a universal law. It's not, usually it's in reference to planets and stars, but it technically can work for any two objects at any two distances. Right? Because notice it's now only in this formula a function of distance and masses. Instead of saying, well, the other way, when we do, the force between two objects, you would have to know what G is. If this was the gravitating object, like the planet, and this was now you out in outer space out here, to figure out what your weight is, mg, you would need to know what is g for this planet out here. It's not 10. That's surface gravity, right? If that was Earth. So that's the idea, is that you have F equals mg. Remember, that's not just used for surface. That's anywhere. Your weight, again, is always just however much gravity force is pulling you towards that planet. It doesn't matter if you're on the surface or you're 3 million miles out floating in outer space. We would still say your weight is mg, but you just say, g isn't going to be the number 10. G is going to be much less. I'll show you how to get that, right? But if g was 6, then for me, I would say, okay, my mass is still 80 kilograms times 6. Wait, I'm only 480 newtons here. Like, yeah, you're only 800 newtons back on the surface of the Earth, where the Earth has a strong gravitational field of 9.8, right? G diminishes as you go out, and so does your weight. So worthy of noting would be that it's an inverse square law, for sure. That's worthy of noting. That the gravitational force is inversely proportional to the square of the distance. And that means if you double distance between the two objects, then the gravity force goes down, right? More distance makes less force, times 4, because of this 2 squared effect, right? So that means 2 times further apart is 4 times weaker of a gravity force, or 3 times further apart is 3 squared, 9 times weaker of a gravity force, or 10 times further apart is 10 squared, or 100 times weaker of a gravity force. And it works in the other direction. Of course, if someone says we're going to take these two things and move them 2 times closer, we start out 100 million miles apart, like us and the sun, and we're going to move the sun and one of them so that the sun and the Earth are now 50 million miles apart. So we're making them 2 times closer. It's still the same effect. R is now, this R here is actually getting smaller. We're moving them closer, which tells us the force between them needs to do the opposite, get bigger. They're inversely proportional. So if you make the distance between them 2 times smaller, or half as much, it's a better way of saying it, I suppose, then 2 squared, 4 times stronger of a force. Gravity is 2 times stronger when they're twice as close. What if they go 3 times closer than they originally were? They started at 100 million miles apart, and now they're only 33 million miles apart. That's 3 times closer, 3 squared, 9 times stronger of a gravitational force. It's the same ideas as we said before when they're going the other way, just the reverse, right? Also worthy of noting that that graphically would look like any inverse graph does. All inverse graphs, if we were graphing FG versus R, like this. It's an asymptote, vertical asymptote, horizontal asymptotes, indicating that the further and further you get away, R is now being plotted on a graph. For an astronaut, let's say it's getting further and further away from the planet. What's happening to their weight? It's going down it's riding down this curve, getting closer and closer to 0. It will never reach 0 because it's a horizontal asymptote, which means no matter how far away you go from Earth, you'll still have some amount of Earth's gravity pulling you back, trying to pull you back towards the Earth, which is why mathematically we consider the Earth's gravity to go forever, just getting less and less and less. And I mean, it could be such a small amount that you would never even measure it or notice it, but it's not 0. So that was worthy of noting. FG versus R, that's what it looks like. Is there anything else worthy of noting about just this topic right here, which is still on the screen? Yeah, it's just the idea that the gravity force is proportional to the product of their masses, or the product of 1. I could have said proportional to M1. I could have said to M2. I could say proportional to M1 times M2. Yeah. So what about if both they say you start with 2 objects some distance apart, and the gravitational force between them is 1,000 newtons. Then moments later, mass 1 doubles and mass 2 doubles. What is the new gravitational force? The distances aren't changing, but M1, M2 is doubled. Well, if M1 is going up times 2, that alone should double my gravity force. Oh, M2 doubled also. That alone should double my gravity force. So what are we talking here? We're talking about a factor of 4, right? 4 times more 4, both double up. What if only just one of them doubled its mass? Well, then the gravity force would double. All right. I don't think I'm going to say much more about that. I am now going to talk about finding G. G is usually we call it G prime. So usually when we refer to surface gravity, we just write that as G, and it's a point on the surface. For Earth, we would say 10 meters per second squared. But when they say, what about what is the value of Earth's gravitational field way out here? G is, that's what we say, value of Earth's gravity, how strong its gravity field is. We usually call those G prime. G prime just means some other value other than the surface gravity. So usually we would use this formula if you were trying. G prime is equal to G times the mass of the planet or the sun or whatever the gravitating object is, divided by r squared, where r, remember now, goes from the center of that gravitating object out to wherever that point of interest is, r. Or if you're on the surface of the Earth, then, well, that's r. Worthy of noting, G is proportional to 1 over r squared, right? So if you go twice as far away, 2 squared is 4, it should be 4 times less gravity. G should be 4 times less. So for us, if we live out at r, which we do, and then they mention there's somebody out here in outer space at a distance of 2r, what would 2r, right? R plus r. What would G be out there? Now, about 2.5 meters per second squared, right? Because I'm twice as far away as I am when I'm living on the Earth, on the surface. I've doubled my distance, doubling this, 2 squared, 4. It's an inverse relationship, so it's not, G is going to go up by 4, it's going to go down by 4. 10 divided by 4, bada bing. Right? Or if it was 3 times 3r, way out here, 3r, well, 3 squared, 9 times less gravity, acceleration due to gravity, 10 divided by 9, and whatever you get, 1.1 or something like that. That's how that works. Also note that's, if you forgot the formula, all you're doing is just equating those two formulas, mg and universe, and because, if you're sitting on the planet like this, we know that you can represent your weight down as mg, or we can represent your weight down as gmu times mass of the Earth divided by r squared, which is this distance from the center to you, r, right? So we could use either of those formulas to model how much gravity force you feel in the downward direction towards Earth. Since they both represent Fg, you just set them equal. Mg equals Gm over r squared. Just notice the little m is your mass, which cancels. Thank goodness, G doesn't depend on your mass, it only depends on the Earth's mass. That's all you do to get that result. If you forgot it, it's certainly not on the equation sheet. You're just equating mg, which is on the equation sheet, to gmm over r squared, which is on the equation sheet, and having the awareness that those are both representing the force of gravity, I can just set them equal and boom, cancel out m. There's the formula for G. So that's that. Is there anything else to say about that? I don't know. I don't think so. Oh yeah, I mean, I guess I didn't apply it to the surface of the Earth. So when you use that formula, it can be used for anything. G is literally Gm over r squared for all objects. You can find out what G is on the surface of the moon by just doing capital G, which is the gravitational constant. That's not low G, 6.67 times 10 to the minus 11. Plugging in the mass of the moon, plugging in the radius of the moon squared, and boom, calculate it, and boom, 1.6 pops out to G for the surface gravity of the moon. So when you're applying this to not outer space, because it's versatile, you can use this formula to find G out in outer space. You can use it to find it out once on surface gravity, G on the surface. Then just be aware that that means that r is just the distance from the center to you, and we would put the radius of the planet there. Also, I guess worthy of noting, sometimes their questions reference the densities of planets. It's very rare, but it has happened before. The density formula is rho. That's mass of the planet divided by the volume of the planet. Mass over volume is how much mass exists in a certain volume of space. That would be units of cubic meters for volume and kilograms for the mass of the planet. So the units for density are kilograms per cubic meter. And if they're giving you a planet problem relating to density, the volume technically of a sphere, right, these are spheres we're talking about, is actually 4/3 pi r cubes. So just be aware Very rare chance that that's going to come into the exam. That either of these, the ideas or the volume formulas, very rare. In fact, this formula I believe is on their equation sheet, 4/3 pi r cubed. Density, I do not believe is on the equation sheet. You should know that's just mass over volume. All right, and now I'm going to move on to a couple other things, and then we'll end it. Not too much longer. I guess the quick thing to talk about is orbits. So if this was the Earth again, and there's, I don't know, the moon, this is representing the moon's orbit. We could comment that there's some potential energy. I might as well mention it right now. The potential energy between the moon and the Earth is actually G times the mass of the Earth times the mass of the moon over R squared, where R goes from the center of the Earth to the center of the moon. Technically, there's a minus in there. It's on your equation sheet, by the way. Oh, I didn't mean to write R squared. It's just R. So the force has an R squared in the denominator. The potential has potential energy is just R. There's a minus in there just because of this weird rule they made in physics that all potential energies are going to be minus. And that as you get further and further away from an object, I mean, know that if the moon goes further and further away, it's definitely increasing the potential energy of the moon, okay? Because if it then was released and it didn't have any sideways tangential speed, it would just start flying straight in towards the Earth. And it had further distance to fly towards the Earth, and that means more kinetic energy is going to be created, right? It's because at those further away distance, it has more potential energy. It's no different than lifting a basketball and saying, hey, it's got further to fall, so there's more potential energy. Even in outer space, as they get further and further away, the potential energy goes up. So I don't want the negative sign that's in here to confuse you. It's a weird system they created in astronomy so that out at infinity, if I took this moon all the way to infinity and asked what is the potential energy out there, we would actually say 0. And the reason is because at an infinite distance, there's no force. The gravitational force that we said was gmm over r squared. If I actually stick infinity into r, then that actually goes to 0. So if I was infinitely far from the Earth, which is just a hypothetical idea, then technically the gravity force from the Earth would be 0. And that means I don't have the potential to fall anymore because there's no force. I'm so far away that there's no force pulling me towards the Earth anymore. I don't have to worry about ever being pulled back. I have no potential to fall anymore. So the potential energy is actually 0 at infinity. I know it's a weird thing. Don't worry about those details. Just know that also the potential energy in between infinity, them being infinitely far apart, and where the moon really is, those are all negative. They're considered negative values, negative of this expression here, GMM, the product of the two bodies over R, which is the distance between them. And that as the moon gets closer and closer to the Earth, it becomes a larger negative number. And then as you go further away, the moon goes further away, it becomes a smaller negative number. And then when you're out at infinity, the potential energy is 0, because of what I was saying. U equals 0 at infinity. So in this weird system they've created, all the potential energies are always negative. They still get the potential energy still increases in the system they've created as the moon gets further and further away, because technically a smaller number like -5 is technically compared to a larger negative number like -20. If someone said, and this would be joules, of course, we're referencing energy. If someone said which numbers are -5 joules or -20 joules, technically -5 is a bigger number. It's closer to 0, right? -5 is a bigger number than -20. And so that means as we go further and further out, it becomes -4 joules, -3 joules, -2 joules, which is greater than the potential energy it has when it's really close. See, it's weird. I know it's a crazy system they created. And at infinity, it's 0. Don't let that confuse you. It's not important. The only thing that's important is the formula. Recognizing that it's the same formula as gravity force, just an R on the bottom. And the same idea that as two planets get further and further apart, the potential energy increases. If they're allowed to fall towards each other, then that potential energy turns into kinetic energy, as we would always expect, right? How about orbits? Is it worth mentioning those now? No, probably not. I guess I would lastly say, if we go back to this, I mean, I was thinking like elliptical orbits. I'm going to do that in another lesson. That'll be hopefully a short one, because I'm nearing the end of this whole circular motion. After this, it's pretty much Kepler's laws. That's it. I'm done with all dynamics. Whew. But I'm not fully done. I will point out, they said this was the Earth and this was the Moon again out here. If their question was relating to the speed of the Moon, the orbital speed of the Moon, this is a distance r, and it has some orbital tangential speed v, which prevents it from falling straight towards the Earth. Know that, again, if they said draw the free body diagram for this moon, for the Moon, it's just the gravity force pulling straight in. Is that a centripetal force? Yeah, it's pulling straight towards the center of the orbit, right? That's a circle. This orbit is a circle, right? And so that means we can fold right away into that discussion centripetal force and centripetal acceleration, right? So that means what again force is providing the centripetal force to the Moon? Earth's gravity force. What is Earth's gravity force? It's equal to the mass of the Earth times the mass of the Moon over r squared. We knew that already, right? And if Earth's gravity force is actually a centripetal force, and it is a centripetal force, then we should be able to say we can equate Fg to Fc, because it is Fc. Where this m, v squared over r, that m is always the thing that's in orbit. So that would be the Moon, mass of the Moon, right? So I technically can be aware that the mass of the Moon times the velocity of the Moon squared over the distance all the way out from Earth all the way to Moon, r, is equal to g times the mass of the Earth times the mass of the Moon all over r squared. Be aware that equating these two happens a lot for this topic. Taking the centripetal force equation and setting it equal to the gravitational force equation, since the gravitational force is providing the centripetal force in exactly the amount of mv squared over r. So out at the Moon, the amount of force between the Earth and the Moon equal to gmm over r squared. Numerically, whatever it is, if it comes out as 1,000,000 newtons, when you do the mass of the Moon times the velocity of the Moon squared divided by r, it still also comes out as 1,000,000 newtons. The Earth's gravitational force is finely tuned at that exact distance so that the amount of gravity force is exactly equal to what the Moon needs to stay at the same distance, moving at a constant speed round and round. Perfect. It's been perfectly designed and created. So when we do that, notice that the mass of the Moons cancel. If I multiply both by r and r cancels. And then on the right side, this r and one of these r's cancel. And essentially I'm left with, I'm going to kind of put a box around it. This is what I'm left with. This is the velocity of the Moon. So this is the orbital velocity. Equals g times the mass of the gravity object, whatever this thing it's orbiting. Mass, I'll put Earth here, over r square rooted. So that's an orbital velocity formula. Gm over r square root. Could have written it like that. Gm mass of Earth over r. Again, that is, oh, I put an equal sign in between them. That is the formula for any orbital speed for any planet, for all of our planets in our solar system, assuming that Sun is now the gravitational object we're talking about, and all the other planets are orbiting around it. The speed of all the planets can be determined by doing this capital G, the mass of the Sun in this case, and r would be the orbital distance for any of the planets, right? 1 AU, 2 AU, 5 AU, 10 AU, 20 AU, up to wherever, how far out you're going. AU is astronomical unit. They don't actually talk about that in this topic. They just use distance as meters. But an astronomical unit is just a distance between us and the Sun, 100 million miles. Worthy of noting that based on this result, that the orbital speed is proportional to 1 over the square root of r, right? Because that's a square root formula that I derived in the bottom. The r is in the denominator, so it's got to be a inverse proportion with 1 over r. What would that look like as a graph? I did this with you guys back then. I plotted it all out and type print, you know, and showed you what it looked like. You might remember. And I had all of the planets' velocities plotted versus r, and I had put it in AU. What was the shape of the graph? Oop, 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 oop. It was an inverse proportion graph, inversely proportional graph. Why? Why is it inversely? Because they're inversely proportional with a square root involved. But just know that it doesn't matter if it's a 1 over r, or it's 1 over square root of r, or it's 1 over r squared. All of those graphs, 1 over r, it doesn't matter what the exponent is, right? Because 1 over r is like r to the 1. 1 over root r is like 1 over r to the 1/2. 1 over r squared, of course, is 1 over r squared. So what's happening when we compare those on the bottom right of the screen right now? We got, you know, r to the 1, r to the 1/2, r squared. What the exponent is doesn't matter. As long as it's a 1 over r relationship, then the shape of this graph will always be the same. It'll always look like I had drawn. 1 over r squared is going to probably go down a little, for sure, more quickly than if it was like this, which would be like 1 over square root of r, because how rapidly that function decreases depends on how quickly the denominator increases, right? If you put in an r in the denominator and square it, it becomes big very, very quickly. And 1 divided by something that's big very quickly becomes small very quickly. And that's why this graph for 1 over r squared would come down like this. 1 over square root of r, that would decrease less quickly. Bottom line, do they all have the same shape with a horizontal asymptote along the x-axis? Yes, you need to know that. That's the orbital velocity profile. After orbital velocity, I don't think there's much more to say or do, although it just makes sense. I know it's been a long lesson and I want to take a break, but you know, to make another lesson out of Kepler's law, I might as well just do it. It just takes, I'm not going to say a whole ton about it. Or maybe I will. I'll just, yeah, I say that and then I'll end up talking 10 or 15 minutes about it. Wish I could just say it in 2 minutes, but there's 3 laws. I guess I'll just go over them in the next lesson. But that pretty much, if I happen to think of other things, I mean, I made a list here. Happen to think of other circular motion things. Oh, there is one. There is one. This one. You need to be aware of this. This comes up on the exam. When you're coming down a ramp and then you go over a hill, right? So this is like somebody that's coming down a ramp again, and then they say it's going up over the hill like this. This isn't, of course, a space thing. This is just back to the circular motion thing. It's the opposite of going around the loop at the top. It's going over a bump. Remember, the normal force is still up, and the gravity force is still down here. If they wanted you to model that, and you need to know that it's still circular motion. It's not a full circle, but you can inscribe a circle with a radius r into that, like I did. That means circular motion still applies. FG would still be plus since it's towards the center. FN would be away since it's negative since it's away from the center. And we would write F net equals mg because that's towards minus Fn. Well, the net force has to be equal to mv squared over r, right? Mass of the yacht, whatever this block is, it's sliding down. V is its speed at this particular point that it has. R would be the radius of that curvature of radius. Radius of curvature. I don't know why I say that backwards sometimes. That's the radius of that curvature. You know, it would be a little bump like this, and then that would be a small radius curvature where, you know, it could be more extended in terms of its bump length, and that increases the radius curvature. So that's the R, and then again we'd have, you know, equals mg minus Fn. This is how you model the forces going over a bump. Again, notice it's just, you know, it's the same thing. You just have to apply the idea that the net force is mv squared over r, and then you just have to do your free body diagram like I did, and then just think, okay, you know, you know, towards the center plus, if it's away from the center minus, just put them in like I did. Maybe I wrote it backwards, so I don't want to confuse you. F was mv squared over r, so I'd write mg, which is plus because it was down towards the center, right? And then Fn is up and away, so that's minus Fn equals mv squared over r. And if they said solve for the normal force, that's usually what the question is. Likely you could move Fn to this side, move this to the other side. You'd end up with Fn equals mg minus mv squared over r. Notice it's similar, but not quite the same as the other ones, but similar. For the loop-de-loop problems, remember the vertical plane? We had the tension at the top was mv squared over r at the top, minus mg. At tension at the bottom equals mv squared over r plus mg, plus because there's always more tension at the bottom. And now we're looking at this derivation for the normal force. It's close. I mean, it's similar. It's got mg and mv squared over r, just like the other ones, but is it exactly the same as either of them? It's not. There's only one that has a positive mg, and it's this one. But this one also has a positive mv squared over r at the bottom right of the screen. This one that I just put the box around as a negative. So that's just how it works. What's the main idea? The normal force becomes less than what you weigh. This is what you weigh, right? If this box that we've said is sliding down, this was just sitting on the road, and someone says, what's the normal force? Well, what's its speed? It's just sitting on the road. So V is 0. Oh, so you put V into this boxed equation, that term goes away. Oh, the normal force is just mg? Yeah, it has to be because it's in balance, right? With gravity. However, the point is when you go up and over a hill, your butt like comes off of the seat. If you go fast enough in a car, really speed up as you feel like a bump like this coming up, really try to speed up over it. You'll feel your body literally come up out of the seat for a brief moment as you ride over the top of that. And then as you come down toward the bottom that I'm drawing over here, you sink back into the seat, and all of a sudden you end up with a force underneath your rear end. That's the normal force. That's stronger than what you weigh. It's more than what you weigh. So when you're coming over the top of the hill, again, your own inertia kind of your inertia, because remember, your speed is in this direction. And so that when your car comes down, just moments after the top, your body actually tries to continue in a straight direction while your car actually goes straight or down. Your body tries to stay moving straight. And that lifts your butt a little bit for a brief moment. It gives you that sense of floatingness just for a second. And then moments later, you get smushed into your seat, and then you get a normal force that ends up being, now you're at the bottom of a hill, and then it would become returned to this when you're coming into the bottom of this hill, all the way on the far right of my screen. When you're coming into the bottom of that hill, it returns to the formula that we had before. Now it'd be your weight plus m over r, something more than what you weigh. But when you're coming over the top of the hill, it's actually what you weigh, mg, minus mv squared over r. It depends on how fast you're going. Like how do you feel on, we're talking about the force between your rear end and the seat. That's the normal force. Depends on how fast you're going, depends on the radius of the circle, right? So if V is really high as you go, then there's even less normal force, because that'll be minus a large number of V squared, right? And that'll make even less normal force. Or if R is really small, if R is a small value, then that's going to cause the overall term mv squared over r to become large. And that means minus mg minus a large number. It means, again, it's going to make you feel really light on your butt for a brief moment if V is either really high or if R is really small. That's it. I don't think I'm going to say anything else. I do know, like I said, in the next lesson, I'm pretty much going to just do Kepler's laws. Hopefully I can do it in 10 minutes, 3 laws, and then Kepler's law, t squared is proportional to r cubed. Know a little bit about that. Elliptical orbits. I know that the total mechanical energy is constant as it orbits around some gravitational object. And then at greater distances. In fact, you know what? I'm going to just finish. It's only going to take 2 minutes because I just want in my own mind that I'm done with this whole unit. So Kepler's laws now. This would be on a comet. We call these elliptic paths. And the force, you know, I'm trying to think because I hate getting upstairs right now. Maybe it's not best. Maybe I should just. I am. I'm sorry. I'm just gonna take a break. I'll come back, and I'll do coupler's lock. Hopefully in like 10 minutes, less than 10 minutes, and but then as soon as that's done, that'll be lesson number 6, and I'm gonna try to hammer through um, energy and momentum because that's actually, and I might actually be able to do both of those in 1 hour and 15-minute lesson, both energy and momentum. That'd be nice. That's what I'm gonna try to do. All right. That's it, guys. That's it for now. See you soon.